Welcome to this comprehensive guide on the Sine of Difference formula, one of the most important trigonometric identities you'll encounter in mathematics. This formula is a powerful tool that allows us to break down complex trigonometric expressions into simpler, more manageable parts. Here is the Sine of Difference formula. This elegant equation tells us that the sine of the difference between two angles A and B equals sine A times cosine B minus cosine A times sine B. On the left side, we have sine of A minus B. This represents the sine of the difference between two angles. Instead of trying to calculate this directly, which can be quite difficult, we can use the right side of the equation. The right side breaks this down into four trigonometric functions. The first term is sine A times cosine B. This represents one part of how the two angles interact when we subtract them. The second term is minus cosine A times sine B. Notice the negative sign here. This is crucial, and often where students make mistakes. The subtraction in the angle difference creates this negative term in the expansion. You might be wondering why this formula is so important in trigonometry. There are several key reasons that make this identity absolutely essential for any student of mathematics. First, this formula allows us to find exact values for angles that would otherwise be very difficult to calculate. For example, we can find the exact value of sine 15 degrees by expressing it as sine 45 degrees minus sine 30 degrees. Second, it helps us simplify complex trigonometric expressions by breaking them down into more manageable parts using angles we already know. Third, this formula is essential for solving trigonometric equations where the unknown angle appears as part of a difference. Finally, it serves as a building block for proving other important trigonometric identities, making it a cornerstone of trigonometric mathematics. Throughout this video, we'll derive this formula step by step so you understand where it comes from. Then we'll work through three carefully chosen examples that increase in complexity, helping you build confidence and mastery. We'll also discuss common mistakes students make and how to avoid them, plus explore some fascinating real-world applications. By the end of this video, this formula will become second nature to you. You'll understand not just how to use it, but why it works and when to apply it. So let's begin our journey into mastering the Sine of Difference formula. Here's the Sine of Difference formula. This fundamental trigonometric identity allows us to find the sine of the difference between any two angles. This formula states that the sine of A minus B equals sine A times cosine B minus cosine A times sine B. Now, let's break this formula down into its components to understand what each part means. In this formula, A and B represent any two angles. These can be measured in either degrees or radians. Notice how A appears in orange and B appears in teal throughout the formula. This helps us track each angle as it appears in different trigonometric functions. Now let's examine each term in the formula separately. The first term is sine A times cosine B. This represents the sine of the first angle multiplied by the cosine of the second angle. The second term is cosine A times sine B. This represents the cosine of the first angle multiplied by the sine of the second angle. Pay special attention to the minus sign between these terms. This is what makes this the difference formula, distinguishing it from the sine of sum formula, which uses a plus sign. This formula is a cornerstone of trigonometry with wide-ranging applications in mathematics, physics, and engineering. Remember this formula well. It will be your key to solving many trigonometric problems and understanding more advanced concepts in mathematics. Now that we know what the Sine of Difference formula is, you might be wondering where this formula actually comes from. While we won't dive into a complete rigorous proof, understanding the derivation helps you remember the formula and apply it with confidence. The first approach uses the unit circle and the distance formula. This geometric method gives us a visual understanding of why the formula works. We start with the unit circle, where every point is exactly 1 unit away from the center. This circle helps us visualize angles and their corresponding sine and cosine values. Let's mark two angles on our unit circle, angle A shown in orange and angle B shown in teal. Each angle corresponds to a specific point on the circle. The coordinates of these points are cosine A, sine A for the first point, and cosine B, sine B for the second point. This is the fundamental relationship between angles and coordinates on the unit circle. Now, the angle A minus B represents the difference between these two angles. This creates a third point on our circle with coordinates cosine of A minus B, sine of A minus B. The key insight is that we can use the distance formula to find the distance between any 2 points on our circle. When we apply this formula to our specific points, the algebra leads us directly to the Sine of Difference formula. The second approach uses Euler's famous formula, which connects exponential functions with trigonometric functions. This method is more advanced but provides elegant algebraic insight. Euler's formula states that e to the I theta equals cosine theta plus I sine theta. This remarkable equation allows us to treat trigonometric functions as parts of complex exponentials. Using the properties of exponentials, we can write e to the I times a minus b as e to the ia times e to the negative ib. When we expand both sides using Euler's formula and equate the imaginary parts, we get our Sine of Difference formula. Understanding where formulas come from is incredibly valuable. It helps you remember the formula more easily, builds your confidence when applying it, connects trigonometry to fundamental principles of geometry and complex numbers, and prepares you for more advanced mathematics where these connections become even more important. Whether derived through geometric reasoning with the unit circle or through the elegant algebra of Euler's formula, we arrive at the same beautiful result. Sine of A minus B equals sine A cosine B minus cosine A sine B. Now, we'll work through our first example. We want to find the exact value of sine of 15 degrees. This is a perfect opportunity to apply the Sine of Difference formula. The key insight is that we can express 15 degrees as the difference between two special angles that we know well, 45 degrees minus 30 degrees. So we can write sine of 15 degrees as sine of 45 degrees minus 30 degrees. Now we apply the Sine of Difference formula. Remember, sine of A minus B equals sine A cosine B minus cosine A sine B. Substituting A equals 45 degrees and B equals 30 degrees, we get sine of 45 degrees times cosine of 30 degrees minus cosine of 45 degrees times sine of 30 degrees. Now we need to substitute the exact values for these trigonometric functions. We need the exact values for these trigonometric functions. Sine of 45 degrees equals square root of 2 over 2. Cosine of 30 degrees equals square root of 3 over 2. Cosine of 45 degrees equals square root of 2 over 2, and sine of 30 degrees equals 1/2. Now we substitute these exact values into our expression. When we multiply these fractions, we get square root of 2 times square root of 3 over 4 minus square root of 2 times 1 over 4. This simplifies to square root of 6 over 4 minus square root of 2 over 4. Remember that square root of 2 times square root of 3 equals square root of 6. Finally, we can combine these fractions since they have the same denominator. Our final answer is square root of 6 minus square root of 2 all over 4. Therefore, the exact value of sine of 15 degrees is square root of 6 minus square root of 2, all divided by 4. This demonstrates the power of the Sine of Difference formula in finding exact values for angles that aren't directly on the unit circle. Now we'll work through our second example, which demonstrates how the Sine of Difference formula can be used to simplify complex trigonometric expressions. Our goal is to simplify the expression sine of alpha plus beta plus sine of alpha minus beta. This type of expression appears frequently in trigonometry, and the sine formulas give us a powerful way to simplify it. To solve this, we'll apply both the sine of sum and sine of difference formulas. Let me first remind you of these formulas. The sine of sum formula tells us that sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. And the sine of difference formula tells us that sine of alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta. Notice the key difference is the sign between the terms. Now let's apply these formulas to our original expression. We'll substitute each formula into our expression step by step. Step 1. We start with our original expression, sine of alpha plus beta plus sine of alpha minus beta. Step 2. Now we substitute both formulas. The first term becomes sine alpha cosine beta plus cosine alpha sine beta. The second term becomes sine alpha cosine beta minus cosine alpha sine beta. Step 3. Now we can remove the parentheses and look for terms that will cancel out. Notice that we have sine alpha cosine beta appearing twice, and cosine alpha sine beta appearing once with a positive sign and once with a negative sign. These terms will cancel each other out. Step 4. The positive cosine alpha sine beta and negative cosine alpha sine beta cancel each other out completely, leaving us with just the two sine alpha cosine beta terms. Step 5. Now we combine the remaining like terms. We have sine alpha cosine beta plus sine alpha cosine beta, which equals 2 sine alpha cosine beta. Therefore, our final answer is that sine of alpha plus beta plus sine of alpha minus beta equals 2 sine alpha cosine beta. This is a much simpler form than our original expression. This example shows the power of trigonometric identities. By applying the sign of sum and difference formulas, we transformed a complex expression into a much simpler one. This technique is extremely useful in calculus, physics, and engineering applications. Now we'll tackle our most challenging example. We need to solve the trigonometric equation sine of x minus 30 degrees equals 0.5. This type of problem shows how the Sine of Difference formula becomes a powerful tool for solving equations. The first step is to apply the Sine of Difference formula. We know that sine of a minus b equals sine a cosine b minus cosine a sine b. So sine of x minus 30 degrees becomes sine x cosine 30 degrees minus cosine x sine 30 degrees. Next, we substitute the known values for cosine 30 degrees and sine 30 degrees. Cosine 30 degrees equals square root of 3 over 2, and sine 30 degrees equals 1 over 2. These are fundamental trigonometric values you should memorize. Now we need to solve this equation algebraically. We can factor out common terms and rearrange to isolate the trigonometric functions. This equation can be written as square root of 3 over 2 times sine x minus 1 over 2 times cosine x equals 0.5. This equation has the form a sine x minus cosine x equals 1, where a equals square root of 3. We can solve this using the identity that relates sine and cosine. We'll use the technique of expressing this in the form r sine of x plus phi equals 1. Now we can rewrite our equation as 2 sine of x minus 30 degrees equals 1. Dividing both sides by 2 gives us sine of x minus 30 degrees equals 1/2. This is exactly the form we started with, which confirms our approach is correct. To find the values of x, we need to determine when sine equals 1/2. We know that sine of 30 degrees equals 1/2, and sine of 150 degrees also equals 1/2. Therefore, x minus 30 degrees equals 30 degrees or 150 degrees, giving us x equals 60 degrees or x equals 180 degrees. This example demonstrates how the Sine of Difference formula transforms a complex trigonometric equation into a more manageable form. By applying the formula, substituting known values, and using algebraic techniques, we successfully found that x equals 60 degrees or 180 degrees. This approach is essential for solving many types of trigonometric equations. Now that we've worked through several examples, it's crucial to understand the most common mistakes students make with the Sine of Difference formula. By recognizing these pitfalls, you can avoid them and build confidence in your trigonometric problem-solving skills. The most common mistake is mixing up the sine of sum and sine of difference formulas. These formulas look very similar, but there's one crucial difference that changes everything. The key difference is in the signs. For sine of a minus b, we have sine a cosine b minus cosine a sine b. For sine of a plus b, we have sine a cosine b plus cosine a sine b. Notice how the middle sign changes everything. Here's a helpful memory tip. The middle sign in the formula always follows the operation in the angle. If you have a minus b, the middle term is minus. If you have a plus b, the middle term is plus. Success with trigonometric identities requires memorizing the exact values for special angles. These 5 angles appear constantly in trigonometry problems, and knowing their sine and cosine values by heart will save you time and prevent errors. 0 degrees, sine is 0, cosine is 1. 30 degrees, sine is 1/2, cosine is square root of 3 over 2. 45 degrees, both sine and cosine equal square root of 2 over 2. 60 degrees, sine is square root of 3 over 2, cosine is 1/2. 90 degrees, sine is 1, cosine is 0. Here are 4 essential tips that will help you master the sign of difference formula and avoid common mistakes. First, always verify your answer by checking special cases. If your result doesn't make sense for simple angles, you've likely made an error somewhere. Second, write out the complete formula before substituting any values. This prevents you from accidentally using the wrong formula or making sign errors. Third, double-check all signs, especially that crucial middle minus sign. This is where most errors occur, so take an extra moment to verify. Finally, practice with different angle combinations regularly. The more you work with these formulas, the more natural they become, and the fewer mistakes you'll make. Remember, the sign of difference formula is sine A cosine B minus cosine A sine B. Master this formula, avoid the common mistakes we've discussed, and you'll be well prepared for any trigonometric challenge that comes your way. Now that we've mastered the sign of difference formula through examples, it's time to explore its incredible real-world applications across multiple fields of study and professional practice. The sign of difference formula finds applications in 4 major fields. In mathematics, it simplifies complex trigonometric expressions and helps solve advanced equations. In physics, it's essential for wave analysis and oscillatory motion. In engineering, this formula is crucial for signal processing and control systems. Computer science applications include graphics programming, game development, and digital signal processing algorithms. Let me show you 3 specific examples of how this formula is used in practice. In physics, when analyzing wave interference, we encounter expressions like this wave equation. The sign difference formula helps us understand how waves combine and interfere with each other. Moving to our second example in engineering applications. In engineering, particularly telecommunications, the sign difference formula is fundamental for signal modulation. Engineers use it to encode information into radio waves and decode received signals. Our third example demonstrates computer graphics applications. In computer graphics and game development, the sign difference formula is crucial for object rotations, animations, and 3-dimensional transformations. Every time you see smooth rotation in a video game, this formula is working behind the scenes. These applications demonstrate why mastering the sign difference formula is so important for your mathematical journey. Mastering the sign difference formula is crucial for several reasons. It serves as a foundation for advanced trigonometry and calculus courses. It's essential for success in physics and engineering programs. This formula is required knowledge for many STEM career paths, and working with it builds your problem-solving and analytical thinking skills that will serve you throughout your academic and professional journey. As we conclude this comprehensive tutorial, remember that practice is the key to mastery. The more you work with the sign difference formula, the more natural it becomes. Start with simple problems and gradually work up to complex applications. Remember, every expert was once a beginner. Thank you for joining me on this mathematical journey through the sign difference formula. If this tutorial helped you understand the sign difference formula, please give it a like. Share your questions or suggest topics for future videos in the comments below. And don't forget to subscribe for more mathematics tutorials that make complex concepts clear and accessible. Keep practicing, stay curious, and remember that mathematics is a powerful tool that opens doors to understanding our world. Until next time, keep learning.